Alright, so here we go. We're going to put a little Christmas bow on our talk with our discussion here on binomial distributions. So looking at this note sheet, what we wanted to look at now is looking at the shape of a binomial distribution. So what we're looking at right down here is we see 5 distribution charts, and with each one of these, the number of people that we were randomly selecting kept on going up. So once you're looking at these here, you can see that we go here, we look at 5 people, and then we go to 10, and then it goes to 25, and then we look at what if we sampled 50 people, and then what if we sampled 100 people. So what this study was doing here is, suppose if we were looking at 5 people randomly selected, the population in the U.S., the number of children were counted, and I guess they're defining children as 13 years or younger. And what they were doing is when they looked at, say, for example, 5 people were polled, they counted the number of children in that group. And when you're looking at this chart here, one thing I'd like you to notice is this first bar graph. There's 0 children. They said, well, in their study here, they noticed that around a little bit over 30%. Here in the study, once they conducted a 5-person study, about 30% of the studies showed that you didn't get any children in the group. And that's kind of what this passage is looking at right here, if we take a step back and take a look at that. It kind of says that right here, doesn't it? So in just over 30%, the 5-person samples, there were no children present. In 40% of the 5-person samples, only 1 child was present. So you can see in this chart right down here, 40% of those studies, you can see with the second bar right there, that's one child. So if you look here at these bars, notice you have 5 bars here for 0, and then 1, 2, and 3, and then you see something right down there with a very, very small percentage of giving all 5 of them. And so notice what happens here as we keep on looking at larger and larger sample sizes is that the data gets more and more and more looking like this guy right down here. So does this look familiar? Yeah, this is our bell curve that we've been dealing with here. And what this bell curve is kind of showing is that the number of children, once they took a sample size of 100, they noticed that about a big percentage of it, so a little bit under 100%, a little bit under 10% right there, the biggest chunk of it, we end up running across 20 children in that set of 100. So as you can see with all these distributions, not all of them were normal. You can look at these ones right. This one right here definitely was not a normal distribution. But as we kept on increasing, it got more and more like that normal distribution that we know and love. And this phenomena is triggered because from the fact that we keep on doing larger and larger and larger sample sizes. So with large sample sizes, the distribution looks more like a normal distribution. So with a large enough sample size, the closer it gets to be a normal distribution. And what we call this right down here, and you put this on your note page, this is called the rule of 10. And what the rule of 10 states is that the shape of binomial distribution will be approximately normal if the expected number of successes is 10 or more and the expected number of failures is 10 or more. Okay? So we can write this here as just a series of formulas, just basically like this. Remember, yesterday we talked about how to calculate the expected number. We take that probability of success and we multiply it by the number of trials. And if we have the number of successes as 10 or more, then we can say that that distribution will be approximately normal. So what we're going to write here is 10 or more. Well, that would be thought of as like this. P times N needs to be greater than or equal to 10. Hey, that kind of rhymes. But also, don't forget here, for a distribution to be approximately normal, the number of failures, the expected number of failures needs to be 10 or more. So I think if I remember right, we define that as 1 minus the probability of success. Remember, the probability here is always expressed as a decimal. So that's why we're using 1 to represent 100%. Multiply that times n. That also needs to be greater than or equal to 10. So in the next video here, we're going to practice a little bit. So here we're going to use the rule of 10 and look at one situation here, and we're going to decide if the sample size is large enough so that the binomial distribution will be approximately normal. So in this given situation here, suppose that about 20% of the population in the U.S. is children. Let's take a random sample of the people in the U.S. and count the number of children present. So what you see along here is just a first example. Suppose the sample size was just 2 people, and we were just assuming the probability of success would be 2 times 0.2. Remember, 0.2 is taking that 20% and writing it as a decimal. We always have to do that when we do the expected value. So we take the number, the sample size, we take n, multiply it by 0.2, we get 0.4. And then if we do the probability of a failure, which is the other side of that 20%, think about it this way. If 20% would be children, then think of it as 80%. So I'm going to use 0.8 times the 2. So 2 times 0.8 gives us 1.6. Now, because of the rule of 10, obviously we are not greater than 10 when we have a number of 0.4. We're not greater than 10 when we have 1.6. Both those values are less than 10. So the sample size is too small. What if we increased it to 10? So now if we take 10 and multiply that by the probability of success, which would be 20%, which we have to write as 0.20, do that math. Hey, 10 times 0.20 just moves the decimal point over 1, so we'd have a 2 right there. So we'll see here, we struck out there for the rule of 10. Since both have to be greater than 10, there really would not be a real necessary move to do the second one for the failures, but if we really wanted to, we take that 10 and we multiply it by the probability of failure. Well, if it's 20% for success, well, that would mean 80%. Oops. Let's erase that. And let's multiply this times 0.8, which would just put it at 8. Since that's also less than 10, is this approximately normal? No, because both of these two numbers here are less than 10. What if we upped it to 25? So now let's take 25, multiply it by 0.2. Well, if we take 25, multiply it by 20%, which is 0.2, I get 5. See, that's bad news for rule of 10. Probability of failure. Take 25, let's multiply it by 0.8, and we get there 20. Now notice we're getting closer here. Still not enough for to say the data is normally distributed because of this problem right here with the 5. How about 50 times 0.2? So 20% of 50, multiply 50 times 0.2, I get 10. Hey, now we're cooking. Get it? Because my last name, okay. And then you take the 50, multiply it by 0.8, and we get 40. So, cool. The rule of 10 works here. So is there enough for this to be approximately normal? Yes, because we're at least 10. So 10 would be acceptable here, by the way. And then here we're more than 10, so that's good. And of course, if we upped it to 100, I'm pretty sure we'd be in good shape here. So 100 times 0.2, well, that's easy. Take 100 times 0.2, that would be 20. So rule of 10, check. And then 100 times 0.8, that would make 80. Check. So rule of 10, there we go. Take a look at this situation. Suppose we were rolling a 6-sided die and, oh, typo alert. Faces out numbers 1 through 4. That's supposed to be 1 through 6. That makes sense, right? Counting the number of 5s, how many rolls would you have to take in order for the distribution to be approximately normal? Well, remember with the rule of 10, we need the probability of success times the number of trials to be greater than or equal to 10. We also need 1 minus the probability of success, which means the probability of failure, times n, We need that to also be greater than or equal to 10. So let's first calculate the probability of success, because we're going to need that for both of these. Well, we're looking for the number times we roll a 5. Well, the 5 is what we're after here as our target, our success. So probability of rolling a 5 would be 1 out of 6. So I'm going to move this over here and start working here. 1/6 times, now the question's asking how many rolls. In other words, how many trials. So n is actually our unknown here, and we want that to be greater than or equal to 10. So this just becomes a pretty basic algebra problem to solve for n. If n got multiplied by 1/6, recall that to eliminate a fraction, you can multiply by its reciprocal, which would be 6 over 1, but we like to just call it 6. 6 over 1 times 1 over 6, that makes 6 over 6, and 6 divided by 6 is 1. And then if we have the 1 here and the 1 there, multiply those together, we're left with n. Now what I do to one side, I have to do to the other. So if I take 10 times 6, that means we get 60 right here. So we'd have to do this one at least 60 times. I wonder what happens if we do the other one. Let's see. So the probability of failure, well, if it's 1 out of 6 for success, then it'd be 5 out of 6 for failure times, and that's me just doing the whole 1 minus the probability. I'm just going to write that as 5/6, and then times that by the number of trials which we're trying to solve, and that needs to be greater than or equal to 10. So the reciprocal here in this case would actually be 6 over 5, because that would make that 30 over 30, and 30 divided by 30 makes 1, so 1 times n, there's our n. So what do I do to one side? I have to do the other. Multiplying by a fraction with a number that's a non-fraction, pretty easy, just slap a 1 under that, and we have 60 over 5. And then if we reduce that fraction here, we get 12. So going back to the question, how many rolls would you have to take in order for the distribution to be approximately normal? For the probability of success, it's 60. Failure, it's 12. So in order for them to both be over 10, I think we'd have to do that, it'd have to be 60 times. Just because this number here, we wouldn't have an expected number of above 10 until we got to our 60th roll. If we went to a 12th roll, we wouldn't have enough for that success there. So when you're looking at this type of move here, once you get down to this point, always take the bigger number.